G'day guys, and welcome back to Up to Speed with Elasticsearch. In the last chapter, we introduced Elasticsearch. We went over some of the basic concepts around what it is, and we set up Elasticsearch so that it was running locally on our machine. And we also imported some data into it that we're going to use to a certain degree, this chapter and future chapters. In this chapter, we're going to be focusing on indexes, which I mentioned in the last video, are kind of like tables in a relational database in the sense that these are the logical units where our data is stored. Before we look at indexes themselves, though, I wanted to actually look at the anatomy of Elasticsearch, look at what's actually under the hood when you run Elasticsearch, just because some of that stuff I think is probably useful to understand before we look at indexes. So to kick things off, an Elasticsearch installation, you could say, has four main parts to it, or there are at least four main terms that I want to cover before we move on to indexes. So at the top here, we've got a cluster. Inside of a cluster, you can have one or more nodes. Inside of a node, or a node, you could say, inside of a node, you have one or more indexes, and an index will contain one or more shards. Now, I'm going to go through each of those terms shortly, but that's basically the hierarchy I suppose you can keep in mind. And we're going to come back to this diagram after we cover the terms. So to start off with, we'll start with a node, because we've actually already seen a node in the last video when we installed Elasticsearch. A node is a machine, physical or virtual, that's running Elasticsearch. So when we installed Elasticsearch in the last video, we were running a node, a single node. So a node can be, as said, a virtual machine, or it could be a container, especially today when you want to be able to spin up new nodes quickly. But that's basically a node, simply put. So a cluster is one or more nodes working together, and I don't want you to think that a cluster has to be at least two nodes. Even if you do only have one node, like we have one node at the moment running on our local machine, we're dealing with a single node cluster. But one or more nodes working together make up a cluster. And why you might have more than one node, well, if you can imagine, a single node or a single machine or a single container has a limited amount of computing power, a limited amount of storage, a limited amount of throughput. So by adding more nodes to the cluster, we're scaling horizontally, and we'll be able to serve more requests and serve more traffic. A document is one that I couldn't fit in the diagram earlier, but a document, you could say, is a record that's stored in Elasticsearch. So from a relational point of view, you might say a document in a document database like Elasticsearch somewhat corresponds to a row in a relational database. But as we said, a document is going to contain nested fields, nested objects, nested collections and things like that, or at least they can. So you don't need to pull data from multiple sources and join them together to create something to actually serve to your users. The data that your application is using can retain its own shape, and that makes up a document. An index, you could say, is a collection of documents. So if you have a data set, be it a Shakespeare data set or an Apache logs data set, or some kind of application domain data set that you store inside of Elasticsearch, you're going to store all of those documents, all of that data inside of an index. And we're going to look at indexes in more detail shortly, but for the time being, you can imagine them as a collection of documents. An index is going to contain multiple shards. So a shard is a physical unit of storage for an index. A shard can be a primary shard or a replica shard. What's the difference between a primary shard or a replica shard? Well, imagine you've got an index running on your node, and you've got all of this traffic coming into your node, and eventually you kind of reach a limit, and you need to scale horizontally. So you add a second node, and what you want is you want to have, say, half of the traffic for adding new documents, adding new data, to go to node 1, and you want the other 50% of ingesting traffic, of creating new documents, adding new data, which in Elastic we call ingesting. You want the other 50% to go to node 2. So you kind of need to split up the physical storage of that data. Half of that physical storage needs to go to node 1, and it has to live in node 1. And the other 50% has to live in node 2. And in that particular situation, where both nodes are responsible for ingesting data, so adding new documents, deleting documents, mutating documents, those physical units of storage that live in node 1 and node 2 would be primary shards, because they're responsible for adding new documents. Replica shards are not really responsible for adding or mutating documents. Replica shards can live on other nodes, but they're just copies of primary shards. They're replicas of primary shards. So if you've got a situation where you've got, let's say you've got a single node cluster at the moment, and you notice that your load is increasing and you want to scale horizontally, but most of your traffic is read traffic. There's not really a whole bunch of indexing going on. It's just a whole bunch of searching. So you can add another node to your cluster, and you want to create another shard of your index. But because most of your traffic is search traffic, you're not really going to have much benefit of storing half of that data on node 1 and half of that data on node 2, because well, when you're doing a search, there's the possibility that some of the data will live in node 1 and some of the data will live in node 2. So at the end of the day, the search requests will need to hit both nodes anyway. What you really want here is a replica shard. So you're going to have all of the data living on node 1 and an exact copy of all of the data again living on node 2. And now when a search request comes in, it can either hit either node 1 or node 2, because the entire shard lives on both nodes. So it doesn't matter which node gets hit for the search request. So that's a replica shard. With a primary shard, you're kind of cutting up your data and storing a subset of your data over here, and another subset of the data over there. Works really well when you want to spread the load of indexing, or spread the load of ingesting, adding new data, or making changes to data. But when you want to spread the load of searching, perhaps what you want to do is add more replicas. So hopefully that clears up the difference between a primary and a replica. To illustrate that, I have here an example cluster with 2 nodes. You can see this aqua-colored node is a primary shard. This is primary 1. And we've got this, I'm not even sure what color you would use here, but this kind of greeny looking color is another primary shard. It's the primary shard. So primary shard 1 and primary shard 2 for the same index. Now, the aqua turquoise, however you describe this, shard here has a replica, which is living in node 2. So the primary lives in node 1, and the replica lives in node 2. We've got another primary shard here for the same index that lives in node 2, and it also has a replica in node 1. So you have an index that contains 2 primary shards and 2 replica shards. And this is kind of a 50-50, you could say, distribution. So you probably have a workload that's sort of evenly distributed between creating new documents and searching existing documents. So I suppose the point that I'm trying to highlight here is you don't want to do something like create as many primary shards as you have nodes just for the sake of it. You really want to consider what your workload is like, and is your application doing more ingesting of data, making changes to data, or is it doing more searching when it comes down to figuring out how many primary shards do I want, how many replica shards do I want. All right, so those are kind of the basic terms that I wanted to cover, and here's that diagram again. So up the top we have a cluster. Our cluster contains nodes. In our example, we have a single node cluster, which is a node running locally on our computer, running Elastic 7.10. In the example earlier, we had 2 nodes. It was a 2-node cluster. You'll have one or more indexes. So in our situation, we've got a bunch of indexes that Elasticsearch created. But then we also have the 2 indexes that we're going to be working on through this course. We have the Shakespeare index, and we have the Apache logs index that we're going to be working with. And each of those indexes are going to contain one or more shards. Now, if we just come back, the shards really should be living on different nodes. And Elasticsearch actually will complain if you try to allocate more shards than you have nodes. So for example, if you only have a single node cluster, like us, and you tell Elasticsearch that, hey, I want 2 primary shards, Elasticsearch will refuse to fulfill that criteria, and your index health will show up accordingly. It won't be in a green health state. The same is true actually for replicas. So Elastic won't let you put a replica on the same node that its primary is on. So otherwise you're kind of defeating the purpose of having the replica in the first place. You're not going to get any throughput benefits, and you're not going to get any resiliency benefits either. If the node goes down, you lose both the primary source of the data and the replica. But if the replica is on a different node and the original node goes down, Elastic can promote the replica to primary, and you haven't lost any data. But if they're both on the same node, then you're getting no benefits whatsoever. So Elastic will not let you do that. So those are shards, and we're going to come back to our indexes that we have locally, because if you remember from the previous video, they were both in a yellow health state. So you might be thinking, well, perhaps the reason they're in a yellow health state has something to do with the number of primary shards and the number of replica shards that Elastic has allocated or is trying to allocate to those indexes. And if you're thinking something along those lines, I think you might be right. So we're going to come back to that at the end of the slides. With that in mind, I think we can start looking at what is inside of an index. So aside from the actual documents, aside from the actual data, you could say that Elasticsearch indexes contain 3 things. They contain settings, which control, for example, the number of shards, the number of replicas, all sorts of other settings. They contain mappings. So just like in a relational database, when you create a table and you specify the columns in that table, each column has a data type. Same thing in Elasticsearch. We have data types for the different fields of our documents. And that's largely what mappings controls. You also have aliases. So you might want to use a single alias to point to multiple tables, or you might want to use an alias in your application code. Instead of using the index name, you can use an alias. That way you're able to version your indexes, and so long as you're using the alias in your application code, your index can change. It can go through multiple versions. Your application code doesn't need to change because it's just using the alias, and you can just use the alias to point to the most recent version. So aliases let you do cool things like that, and we're going to touch on all 3 of those. So to start off with, we'll look at common index settings. So there are so many index settings that are available to you, but I'm only really going to mention the ones that I find myself using somewhat regularly. So the first 2, how many primary shards, how many replica shards? These you'll be using probably every time you create an index. And we've already covered what a primary shard is and what a replica shard is, so I'm not going to go over those again. You also have ingest pipeline settings, which we are not going to cover today, but we will cover ingest pipelines in another chapter. And the same is true for index lifecycle management settings. So these are features of Elasticsearch that we will cover in future chapters, but not today. I do mention them though, just so that you stay on the edge of your seat, so to speak, and look forward to future chapters when we do cover these. Index mappings. So as we said, when you create an index in Elasticsearch, there is a mapping that tells Elastic what data type belongs to what field. Mappings can be done in, you could say, two ways, dynamically or explicitly. So you might be wondering, well, when we imported the data from the dataset using the data visualizer tool in Kibana in the last chapter, we didn't actually specify any mappings. So what happened there? How did Elasticsearch create the mappings for the data that we imported? And the answer to that is they were mapped dynamically. Elastic looks at the shape of the first record that's coming in, and it will try to guess what the most appropriate mappings are for all of the fields. And sometimes that works fine, but in my experience, it almost always gets something wrong. So personally, I'm not a big fan of dynamic mapping, and generally I prefer to keep dynamic mapping turned off, just because if the first document gets mapped incorrectly, you cannot actually change a mapping after it's been created. So I much prefer to do my mappings explicitly, and when I create the index, tell Elastic to not allow any dynamic mappings for that index. What that will mean is that if a document is being saved to the index and you do not have an explicit mapping for a field contained in that document will not be added to the index. So that is something to be aware of. But if you like to be in control of all your fields, you probably prefer that to the alternative where Elastic dynamically maps a field and it maps it incorrectly, and now you've got a big problem on your hands where you need to create another index with the correct mappings and move all the data over. So I much prefer to just turn dynamic mapping off. And one of these settings in the dynamic mapping settings allows you to do that, and we're going to do that when we get to the hands-on section of the video at the end. Explicit property mapping is where you basically cover the different data types for the different fields. And that wraps up my slides. We do have a number of tasks that we're going to do in the hands-on section when we get into Kibana shortly. Maybe let's start with one, and then we'll come back to this slide as we work through them. So the first task that we have is to verify the number of nodes in our cluster. So if you haven't already done so, jump into wherever you've downloaded Elasticsearch and Kibana, boot them up. So from the root of the download, launch bin/elastic and bin/Kibana. At the end of your Kibana output, you should have this HTTP server running on blah, 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 which tells you the port, but it should be 5601. Open up DevTools, and you should see a screen that looks like this. If you're not on this screen, you might need to search for DevTools, and then you should end up on a screen that looks like this. All right, I'm just going to take a sip of water. Okay, so first task. How many nodes are in our cluster? We're going to make another request. You'll notice that unlike Postman or Insomnia or another HTTP client tool, we can actually have multiple requests in our request window in Kibana, which is really cool. And next to each request, there'll be a play button that will let you execute that particular request, which is pretty awesome. You can also add comments as well using a hash, so that will comment out that particular request. So the request that we want to run is to get the number of nodes that are in our cluster. So we can run a get underscore cat and execute nodes. And we're going to use the question mark V to get verbose output so that we get the column headings. Now, if you're on a Windows machine, instead of hitting the play button, you can hit Control Enter. If you're on a Mac, you can hit Command Enter. And that's a nice shortcut that will execute the currently highlighted request. So as we can see here, we've got one node coming back. The IP is my local IP. Few other metrics here. So we're, as expected, running on a single node cluster. So that's task 1 done. Task 2 is we want to create new indexes for the Shakespeare and Apache logs indexes with the replica shards set to 0. Why do we want replica shards set to 0? Well, we're on a single node cluster. We must have at least one primary shard for an index because, as we said, the primary shard is where the physical unit of storage for the data. So that's where the data physically gets stored. So you must have at least one primary shard, otherwise you can't store any data. And that wouldn't make any sense. And as we said earlier, if I come back to the slide, the replica shard cannot exist on the same node that the primary shard exists on. And since we're only on a single node cluster, that basically means we cannot contain a replica. We cannot have replicas. So we need to set our number of replica shards to 0 for our indexes. And that is why if we run get indexes, that is why Shakespeare and Apache logs are showing up in yellow. Just to prove to you that that is the case, if I run a get on Apache logs, notice there's autocomplete with Kibana as well, which is quite nice. If I run a get on Apache logs, and maybe I'll do /_settings, just to get the settings, and I run command enter, we can see here we've got a number of shards set to 1, so 1 primary shard, and we've got number of replicas also set to 1. So by default, Elastic likes to create indexes with 1 primary and 1 replica, but since we're on a single node cluster, that's a no-go. So let's recreate this with 0 replicas. What else did we need to do for that task? Confirm that the index health is now green. So let's go ahead and do that. Let's say we'll do a put, and we're going to want to specify the name of the index. So the name of the index is, let's say, Apache _logs _v1. And we want to specify the settings. And inside the settings, we want the number of shards to be 1, but we want the number of replicas to be 0. And for now, that's all we're going to do. So we're going to run this. Cool. And let's do the same thing, but for the Shakespeare logs, or Shakespeare _v1. Same settings, 1 primary shard, 0 replicas. Let's run this. And let's check our indices again. So we've got Apache logs v1, which is in green health, and Shakespeare v1, which is in green health. Fantastic. As you'll notice in the output here, though, there are no documents in either of them. So we've created the index, but all the data still lives in the old indices, or old indexes. So task 2, looking good. We've got the new indexes. We want to give our new indexes an alias and explicit mappings. And we want to prevent new fields from being dynamically mapped. So it's kind of 3 subtasks here. We'll go ahead and do these. First things first is let's give them aliases. So I'm going to modify this to include an aliases. And the alias that we are going to use here is Shakespeare. I'm not sure I'll be able to use Shakespeare because there's already an index with that name, but let's, just for fun, see if it will work. No, that's right. So I'm just going to use then _alias. In practice, it'd be nice to use Shakespeare, but just for simplicity's sake, let's use Shakespeare alias. After we delete the existing Shakespeare index, we can go ahead and change the name of the alias. So, oh, what's going on there? Shakespeare. Oh, sorry. It's actually complaining because that would be overriding the index. So let's change this to /aliases. Not Shakespeare, Shakespeare. Sorry. You know what? Let's look at the documentation for this. Where are we? Search for index alias. Add index alias sounds good. Okay. Let's go ahead and use this. So slash alias slash Shakespeare. Yeah, that's right. So we'll go with Shakespeare underscore alias. There we go. Okay, and let's just verify that that worked. So get Shakespeare v1, and we can see that we have the alias coming back. No mappings yet, but we do have some settings, and that includes the number of shards. We'll do the same thing for the Apache logs. So put Apache logs v1 alias. We'll go with Apache underscore logs alias. And let's just get Apache logs v1. And the alias is there. No mappings yet. Here are the settings. We can also, of course, use the alias to get this information as well. So we can say get Apache logs alias, and we get the exact same information. So okay, that task is, well, the first part of that task is done. Let's, I think, prevent new fields from being dynamically mapped. So I might also point you to the documentation for this as well. So we'll look at, I think I had a link for it. Dynamic mapping. What we want is we want to look at this dynamic parameter. So let's say put Apache logs alias mapping dynamic. Let's set this to strict. There we go. And do the same for Shakespeare. Notice I'm using the alias now. Cool. All right. So let's just try adding a random document to either of those two indexes, or even we can retrieve these and just make sure that that has been applied. So you can see under mappings, we've got now dynamic is set to strict. So if I try adding a document to either of those two indexes, we expect it to fail because we've set that dynamic mapping property to strict. So I'm going to try putting a document to the Shakespeare alias. So I'll use the underscore doc endpoint and specify the ID. So I'm just going to specify 1. And there are no mappings on this index yet, so I'm just going to try hello world, and I expect this to fail. Fantastic. So it's complaining, saying that mapping is set to strict, and it's not allowed to auto map or dynamically map that property. So that seems to be working. The last task that we had is to set explicit mappings for all of those fields. So I'm not really interested in changing any of the dynamic mappings, but I want the mappings to be explicit. So I'm just going to take the existing mappings, copy paste them, and map them explicitly. So since we're already looking at Shakespeare, properties is the mapping setting that we're after. I'm just going to retrieve the current mapping of the original Shakespeare index. So we can see here we've got a properties child object, and let's just copy everything under properties. I think that looks good. there should be a auto indent feature that we can use here, which is nice. So if I look at the original Shakespeare index, it's got an where are we? It's got an index field, which is perhaps a little confusing. We've also got line ID, line number, play name, speaker, speech number, and text entry, and we're just copying all of those and adding those to the new index that we're putting together. Alrighty, so that's acknowledged, and if I grab the mapping of the alias, we can see that we've got all of those fields explicitly mapped. And we're going to do the same thing for Apache logs. There we go. And let's just make sure we update this to Apache logs alias. Cool. So under the properties is basically everything that we want to copy. So I think that should be about where we want to stop. And let's auto indent this. Cool. Let's run it. And let's change this to _alias. Awesome. So under our mappings setting, we've got dynamic mapping set to strict. So in other words, turned off, as we saw before. Adding new documents with fields that haven't been explicitly mapped will be rejected. And all of the properties with their current existing settings. All right, so we've set up explicit mappings. We've prevented new fields from being dynamically mapped. Now we want to reindex the data from the old indexes to the new ones, and we want to delete the old indexes when we're done. So let's use another Elasticsearch endpoint, which is reindex. So we want the source of this reindex. So basically copy the data from one index to another. In other words, reindex. So the source here is going to be index is going to be Apache _logs, and the destination is going to have an index, and this is going to be Apache _logs _alias. Let's go ahead. Well, first, before we run this, let's check our indexes one more time. So we've got Apache _logs with yellow health. This has 9999 docs, and Apache _logs _v1 has 0, which is in green health. So we want to move 9,999 documents from here to here. Then we're going to delete this. Let's run this. Cool. And we have a total of 9999, so sounds good. Let's check our indexes again. And we have, oh, let's run this again. May take a while for these numbers to update. Well, let's do the same for Shakespeare, and then we'll come back. So we want to reindex from Shakespeare to Shakespeare _alias. Run this again. And we got 10,000, which sounds good because there are 10,000 records in Shakespeare. I suppose it's not great that these counts aren't updating in reasonable amount of time. I'm not sure if there's a way to actually speed that up, but we can search the new indexes just to confirm that there is data there. So let's do a get to Apache _logs _alias /_search. So we're going to look more at searching in the next chapter, but just to show that there is data there, let's run this. Cool, and we're getting back 9,999 matches. Now you're not going to get 9999 results in the response here, but it is confirming that there are 9999 matches. So even though the indices metrics aren't updated, this does confirm that there are 9999 records there. So let's do the same for Shakespeare. Sorry, not let's use Shakespeare underscore alias. And we should see 10,000. Great. Let's just try this one more time. Great. There it is after we've already done it the other way. So yeah, that replication seems to have finished. So let's go ahead and delete these yellow indices. So we're going to delete Shakespeare, and we're going to delete Apache logs. So as you might have guessed, the way that we do that is with a delete HTTP verb. So we use delete Apache underscore logs. Cool. And we'll do the same thing for Shakespeare. Nice. Check our indices again. There should be no yellows. Great. So we've got Apache logs v1 and Shakespeare v1. So with that out of the way, let's go ahead and change these aliases. So we'll add another alias to our indexes. So since we've deleted the Shakespeare index, we can use Shakespeare as an alias now, which is good. Great. And we'll do the same thing with Apache logs. Great. So if we get Shakespeare, whoops, sorry, let me capitalize this. Not because I think you have to, but just because. Let's do Apache logs. We can see that there are two aliases here. I think to delete an alias, you can use Apache logs alias, Apache logs alias. Okay, let's use Apache logs underscore v1. Okay, great. So if I try that again, awesome. So we removed that dodgy alias that we created earlier. We'll do the same for Shakespeare as well. So let's just say get Shakespeare. Cool, we've got these two aliases. Let's just remove the dodgy one that we don't want. Shakespeare underscore v1 alias Shakespeare alias. Delete this and get the index again. Cool, so we've got just the one index, which is what we wanted. Awesome, alrighty, so how are we on our tasks? We've re-indexed, deleted the old index. We want to confirm that the aliases, mappings, and settings are correct on the new indexes. We've kind of already done this. We can retrieve information about an index by using a get and then the index name or the alias name. So for Shakespeare, just like this. You can retrieve only the settings, for example, using /_settings or /_mappings, mapping rather, or /_alias. There we go. And as we saw, we no longer have any indexes with yellow health. So I think that more or less wraps up my coverage of indexes. I know that that was a lot to take in, especially with the different field types, but hopefully we'll get a chance to practice those a little bit more when we look at search in the next chapter. And yeah, the differences between the different field types and how they actually impact search should become a little bit more apparent once we start looking at searching. So thanks a lot for following along, and I will catch you in the next chapter. Bye.